Okay, example number 10. We have a circuit that contains two resistors that are in parallel, resistor 2 and 3, and then that combination is then placed in series with resistor 1, which is also 6 ohms. We're asked to find the equivalent resistance. So if we were to replace all three of these resistors with one single resistance, what would that resistance be? So to find the equivalent resistance, we need to identify the series or parallel combination of resistors and replace them with equivalent resistors. And continue this process until all of the circuit has just one single resistance, which is the equivalent resistance for the network. So what we're going to do is we're going to first solve resistor 2 and 3 and replace them with one resistor. So let's do that first. The resistor 2 and 3 are a parallel circuit, so 1 over R, we'll call this R23, which represents the equivalent resistance of 2 and 3 together, is equal to 1 over R2 plus 1 over R3. So that would be equal to 1 over 6 ohms plus 1 over 6 ohms, which gives you 2 over 6 ohms, or 1 over a third ohm. Does not mean that your answer is 1/3 of an ohm. Remember, you have to take the reciprocal of that. So R23 would be the inverse of 1 over 3, which gives you 3 ohms. So now you can really think of R2 and 3 as one single resistor that has an equivalent resistance of 3 ohms. And it may help to redraw that picture. So I'll do that down below just to help you see this. So I've replaced these two resistors with this single resistor R23. So now you can see that these two resistors R1 and now that equivalent resistance R23 are connected in series. So then now we'll go ahead and calculate that resistance in series. So the equivalent resistance would be equal to R1 plus R2, 3, which is 6 ohms plus the equivalent resistance of that, which is determined, which is 3 ohms. And if you add that together, you get a total resistance of 9 ohms. And you can now think of this as one resistor. So let me go ahead and redraw that once more. And there's your equivalent resistance of 9 ohms. So now going on to part B, we are going to find the currents and voltages throughout this circuit. So to find the currents, we have to really look at it looking backwards. So let's start with this resistor, this equivalent resistance of 9 ohms. So that 9 ohms is going to be drawing a current I through it coming from that battery, and that's the current that's going to be going through this equivalent resistance of 9 ohms. So if I use Ohm's law, the EMF equals IR, our equivalent, then I can find the total current in the circuit, because the total voltage in this is 18 volts. And our equivalent resistance is 9 ohms, so that means our total current will be 2 amps. This total current of 2 amps is the current that is going through the equivalent resistance of 9 ohms, and it also is the current that is going through the battery. That's the total current. Now if you look back to our previous picture here, that current of 2 amps also is the same current that goes through R1 and the equivalent resistance of R23. So that means we can conclude that I1 is equal to the total current, which is 2 amps. And now using Ohm's law, one could determine the voltage drop over R1 and the voltage drop over R23. So the voltage drop over the first resistor would be I1 times R1. So that would be a total current of 2 amps times the resistance of 6 ohms. That means there'll be a 12-volt potential drop over the first resistor. And then if we look now at the second resistor, we could find the voltage drop over 2-3 combination. That's the resistance 2-3. That would be the current, again, I times R23. Again, I and I1 are the same thing. So we'll use 2 amps and multiply by the equivalent resistance of R23 together, which is 3 ohms. So that will give you 6 volts, and you'll notice that that 6 plus 12 gives you a total potential of 18 volts. So hopefully one would realize that the voltage 1 plus the voltage 2, 3 is equal to the total voltage of the EMF, which is 18 volts. So now let's go ahead and use Ohm's law to find the current that goes through each individual part of R2 and R3, working backwards now, because we know that this voltage drop from here to here across resistor 2 to 3 is also the same voltage drop whether you go over just singly resistor 2 or singly over resistor 3. That potential drop of 6 volts is applied to both of them. One common mistake people might make with this is they'll say the total voltage would be 1 plus 2 plus 3. That's not right, because as you go over this entire loop, you could think of it as you increase in 18 joules of energy per coulomb, and then you lose 6 joules of energy per coulomb. Not 6, actually, you lose 12 joules per coulomb over here, and then the last remaining bit is 6 joules per coulomb over this last parallel part of the circuit, and you only really go over one path. Okay, so now let's go ahead and find the current that goes through resistor 2 and resistor 3. Current 2 would be equal to voltage 2 divided by resistance 2. So voltage 2, remember, is the same as voltage over the parallel part 2, 3. And that we determined was 6 volts divided by our 6 ohms, which gives us 1 amp. And similarly, we can say current 3 is voltage 3 over resistance 3, 6 volts also, 6 ohms, and gives you 1 amp. And hopefully you would realize that if you look at this, this should make sense, because current 2 plus current 3 are two parallel branches. There's the current going over this branch, I2, and then here's the current going through this branch, I3, and they should add up to the current 1 that is going into this junction. Let's just call that A. Because that would, if it wasn't true, then it would violate the law of conservation of charge. The amount of charge that flows into a junction must be equal to the amount of charge that flows out of the junction. So I2 plus I3 must be equal to I1. You've got 1 amp plus 1 amp is equal to 2 amps. Hopefully you can conceptualize and see this as you've got 2 amps coming along here through this resistor, and then since both of these resistors have the same resistance, they're going to equally split the 2 amps into two pieces, and that's why they're both 1 amp. And that's it for this example number 10.